This is a computer program written in Python. The function Fibonacci n produces the nth number in the Fibonacci sequence 1, 1, 2, 3, 5, 8, and so on. In the Fibonacci sequence, the first two terms are 1 and 1. Some people start with 0 and 1. And each of the other terms is the sum of the previous two terms. What if I told you that this program, or indeed any computer program, can be written using just two functions? In this video, we talk about combinatory logic. In 1920, Moses Schonfinkel invented combinatory logic. Combinatory logic solves the problem of keeping track of variables in a language by getting rid of variables altogether. In combinatory logic, we have combinators that have certain behaviors. Perhaps the simplest combinator of all is I, which does nothing. I is the identity combinator. Here, X can be anything, including other combinators. For example, if we have the expression I, this reduces to I by the behavior of the I combinator. The combinator K does this. For example, what happens if we have Kixy? By the definition of K, Kix reduces to I, so Kixy reduces to Iy. Then, by the definition of Iy reduces to Y. So, whatever x and y are, Kixy ignores x and outputs y. Note that K takes two objects and returns the first one, while Ki takes two objects and returns the second one. The combinators K and I have combined, hence the word combinator, to produce a different behavior. We did not need to create a new combinator from scratch that takes two objects and returns the second one. Rather, we programmed this behavior by combining the two combinators K and I. We have written our first program using combinators. We can give this program a name. Let us call it the N combinator. This is how combinatory logic avoids variables altogether. Our program is simply a string of combinators. Let us try to use this program to reduce something. We first replace n with ki, because that is how n is defined. We then execute the behavior of k, reducing kikk to ik. We then execute the behavior of I, reducing ik to k. Hence, nkk reduces to k. Notice that we are executing the first combinator in every step, ignoring the others. This is called lazy evaluation. We shall be using lazy evaluation throughout this video. The fact that nkk reduces to the combinator k means that nkk and k have the same behavior. They both take two objects as input and return the first one. We say that nkk and k are extensionally equal. Here we are not defining a new combinator. We are saying that nkk and k have the same behavior. In computing jargon, they are different computer programs that do the same thing. These three combinators all take three objects as input, f, g, and x. Let us focus on b first. B first applies g to x, then applies f to the output of gx. Thus, B performs a composition of functions. Note that the expression gx means the output of applying function g to x. In mathematics, we would write this as g of x instead, and the output of B would be written as f of g of x. Focusing now on C, C applies f to x, then applies the output of fx to g. Thus, applying f to x results in a function which is then applied to g. This is called currying, and allows us to consider all functions to have only one input. Moving on to S, S applies f to x and g to x, then applies the result of fx to the result of gx. In a sense, its behavior is that of B and C simultaneously. Thanks to currying, we can switch from fgx to fgx and back at will. Let's give some examples. The combinator Ci here expects two inputs and applies the second input to the first one. In this example, SBI expects two inputs and applies the first input twice to the second input. Here, SKK expects only one input and returns it, doing nothing. So SKK is extensionally equal to I. SKSK expects three inputs and applies the first input to the application of the second input to the third input. Thus, SKSK is extensionally equal to B. This expression has the same behavior as C, and is thus extensionally equal to it. Note that in this example, we reduced KKFGX to G only after realizing that there is no combinator in front of the expression. This is what we mean by lazy evaluation. We postpone the evaluation of expressions in inner brackets until there are no outer expressions that can be worked out. These examples have demonstrated that the combinators I, B, and C are extensionally equal to combinators involving only S and K. The B's in the expression for the C combinator can each be replaced by SKSK. This is very important because we are going to show soon that the combinators S, K, I, B, and C can be used to simulate any program behavior we want. In other words, every program can be written in terms of these 5 combinators. But since 3 of these 5 combinators are extensionally equal to expressions involving the other 2, any program would then be possible to be written in terms of only 2 combinators, S and K. Here's how we can write any behavior in terms of S, K, I, B, and C. We can treat this as a compiler that compiles any behavior into S, K, I, B, C expressions. Here are a few examples. Here, in fact, we get that n equals ki, as we got before. We have already seen this function before as well. M is the function that applies its input to itself. Note that since we have earlier compiled T to Ci, we may say that V is BCT. This is the way we are writing programs without any variables. This is combinatory logic as Schönfinkel intended. Here we verify that our program indeed works. So far, the only programs that we cannot turn into combinatory logic are those that refer to themselves, like this one. This is akin to a function referring to itself, where recursion would occur. For example, this is how yi would reduce if y were an acceptable combinator. It would go on to an infinite loop. We call y a fixed point combinator because yf outputs a fixed point for function f. Since yf reduces to f of yf, yf is the value x that reduces to fx. Thus, yf is the fixed point of f, the value x reducing to fx. Loops are very important in programming languages, so we seek a combinator expression for y. It turns out that there are many such possible programs that have the behavior of y. In fact, we can prove straight away that if y is a fixed point combinator, then so is SIY. Since yf also reduces to f of yf, SIY and y are extensionally equal. There are two commonly used combinator expressions for y. One was discovered by Haskell Curry, and the other one was discovered by Alan Turing. Let us check that both fixed point combinators do as intended. Since yf reduces to m of CBMF, which in turn reduces to f of m of CBMF, we see that yf reduces to f of yf. Similarly, theta f can be shown to reduce to f of theta f. Either of these two combinators may be used to simulate the intended behavior of y. Let us use the y combinator to obtain a combinator expression for the following example function that refers to itself. We first create a new function, fun', that is just like fun but with an extra input. Let's call it f. And with every instance of the fun function on the right-hand side replaced by this new input. We then find a combinator expression for fun'. This can be done now because fun' does not refer to itself anymore. Then function fun is just y fun'. Let us see this in action. So far, the claim that any program can be written using combinatory logic using only the combinators S, K, I, B, and C is perhaps scarcely believable. We are now going to simulate truth values, numbers, and the data structure using combinatory logic, which will hopefully make our claim more credible. Remember that we still need to implement our Fibonacci program using combinators, and we seem to be very far from that goal. Let us start from true and false. These are called Boolean values. In fact, these are the only Boolean values. Their behavior is easy to describe. The idea is that if we have a function that evaluates to the Boolean value true, then function f is evaluated, while if it evaluates to false, then function g is evaluated. We are thus simulating an if-then statement, branching to one part of the program, function f, if an expression is true, and to another part of the program, function g, if it is false. We have already converted these behaviors to combinators. Let us play a bit with these Boolean values by defining the logical connective not. We want the behavior of not to follow its usual truth table. The behavior of not would thus be the following. By our definitions of true and false, true, false, true reduces to false, and false, false, true reduces to true, which is exactly what the behavior of not should be. See, we are branching to a different evaluation depending on the Boolean value of p. Compiling this, we obtain this. One advantage of programming languages that may be based on combinatory logic, like functional programming languages, is the fact that we can mathematically prove things about our programs. For example, we can prove that not of not p is p, whenever p is either true or false. Remember, this means that p and not of not p are extensionally equal. P may be replaced by not of not p or vice versa, without affecting the behavior of the program. Here's the proof. We cannot continue the evaluation of the program until we know the value of p. We consider both possible values of p. If p is true, then the evaluation would continue like this. If p is false, then the evaluation would be thus, if p is true, then not of not p reduces to true, and if p is false, then not of not p reduces to false. This proves that not of not p and p are extensionally equal. We now simulate ordered pairs using combinatory logic. An ordered pair is usually written like this: x, y. Let us suppose our pair x, y is pair xy. We would surely want to access each of the two objects in the pair, like so. Note the similarity with. Perhaps we can define pair such that this happens. In other words, we would like to have this behavior. then first P would reduce to P true, and second P would reduce to P false. We had already compiled pair previously, and first and second compile to these two. For example, first of pair xy correctly outputs x. We can also, perhaps surprisingly, simulate natural numbers. Assuming we have a representation of 0, we may define 1 as the pair false, 0, 2 as the pair false, 1, and so on. In this way, all non-zero numbers are pairs whose first entry is false. The function 0 should return true if n is 0, and should return false otherwise. So we may define 0n reduces to first n. Of course, we want 0 of 0 to evaluate to true. If we define 0 as I, 0 of 0 would reduce to I of true, which reduces to true. That's exactly what we want. So our definition of 0 works. Obviously, this compiles to 0 is defined as first. All of this happens as long as the numbers are defined in the way we have talked about. That is, 0 is I, 1 is pair false 0, 2 is pair false 1, 3 is pair false 2, and so on. We can shorten these infinitely many positive numbers into one function next. Next of n is pair false n, which clearly compiles to next is pair false. In this way, 1 would be next of 0, 2 would be next of 0, and so on. These are our natural numbers then, which represent 0, 1, 2, 3, and so on. If n is a positive number, then we can prove that it is extensionally equal to pair false n minus 1. So the number before n is easily accessible. It is the second entry of the pair. We are getting closer and closer to the Fibonacci program. But first, we need to simulate the behavior of applying a function n times to some input x. In other words, we want something like this. For example, adding two numbers m and n is the same as applying next m times to n, that is, and this compiles to. We still need to define the function apply though. We can read this as if n is 0, then output x, else output f of the output of apply n minus 1 fx. Since this function refers to itself, its conversion to combinatory logic will involve the y combinator. Brace yourselves. It's a very complicated behavior, so it's a very complicated expression with combinators. But now we have everything in place to write our Fibonacci program. Recall that we want to write a program that outputs the nth number in the Fibonacci sequence 1, 1, 2, 3, 5, 8, and so on. We keep track of our sequence using pairs. Let us first write a function that, given any two consecutive terms of the Fibonacci sequence, outputs the next two consecutive terms of the same sequence. For example, if we give it the pair 1, 2, it outputs 2, 3. Or if we give it the pair 5, 8, it outputs 8, 13. The output is the pair where the first number is the second number in the input pair, and the second number is the sum of the two numbers in the input pair. The function that does this would be the following, which we can compile straight away. Now, all we need to do is to apply next pair n times to the pair 0, 1. Then read off the first number in the resulting pair. For example, if we apply next pair to the pair 0, 1 once, we obtain 1, 1, and the first number of this pair is the first number in the Fibonacci sequence. If we apply next pair to the pair 0, 1 twice, we obtain 1, 2, and the first number of this pair is the second number in the Fibonacci sequence, and so on. So we have this expression. Note that the number 1 is represented as next 0. And this behavior compiles to this expression. So that is it. Each of the functions first apply next pair, pair, and next, have a very specific definition in terms of the combinators S, K, I, B, and C, and other functions or combinators like T and N. But these other functions and combinators are also ultimately defined in terms of the combinators S, K, I, B, and C. So at the end of the day, fib is defined in terms of the combinators S, K, I, B, and C. But that's not all. Since the combinators I, B, and C may each be written in terms of S and K only, the program fib may be written in terms of the S and K combinators only. If you are still watching, then we have a bonus bit especially for you. We have just concluded the previous part by reminding you that we are always able to write any program using the two combinators S and K. But is there one universal combinator with which we can write any program? It turns out that there is. It is called the iota combinator and was discovered by Chris Barker in 2001. With this definition, iota is extensionally equal to I. Iota of iota I is extensionally equal to K. And iota K is extensionally equal to S. Thus, the iota combinator alone is enough to write any computer program. Every combinator expression involving S, K, and I can be transformed into one involving only the iota combinator by performing these replacements. This is one of the most astonishing results in mathematics and computer science. Here's how our Fibonacci program would look like if we used only iota. This video is our submission to the second Summer of Math Exposition. We, Alexander Farrugia and Giorgio Grigolo, wanted to explain the basics of combinatory logic to the world for a very long time. This year's Summer of Math Exposition was the perfect medium to do so. Thank you for watching this video. It really means the world to us.